Hello everybody and welcome to your channel Thermal Engineering Concept and the Principle. In some of the previous episodes we have mentioned important factors for the applications of heat exchangers and the types of heat exchangers and some problems that are arising when using heat exchangers. The flow pattern has a vital importance for the operation of heat exchangers and their feasibility and economic design. In the present episode, I will introduce the efficient flow arrangement in heat exchangers and how can we uh, utilize these arrangements to get the optimum design for heat exchangers. Thank you for your support and encouragement, and I hope that you will continue your subscription to the channel and share the information with your friends to achieve the goals from creation of this channel. Let us go directly to the description of the main objectives of this episode, which is related to heat exchangers and the flow arrangements. The fluid flow arrangement in the heat exchanger, and as we are talking about shell and tube heat exchanger, is the same for other types of heat exchangers. So there are two main types of fluid arrangement in the heat exchanger. The first one is called the counterflow pattern, and the second one is called the parallel flow pattern. In the first type, the fluids on the shell side and tube side enter the heat exchanger from opposite ends of the heat exchanger. Therefore, as they are passing through the heat exchanger, the flow is counterflow. And at the same time, when we talk about the other type, the fluids enter from the same end or the tube and shell sides, and they are leaving at the other end at the same direction. Therefore, these fluids, as they are passing through the heat exchanger, they are following a parallel path. So if we talk about the counterflow heat exchanger, if we have a look at the blue line, which represents the cold fluid, it enters at T sub Ci and leaves at T sub C naught. And when we have a look at the exit temperature, it will be there is a possibility to be higher than the exit temperature of the hot fluid. On the contrary, there is no possibility if we have a look at the right hand side graph, the cold fluid as it enters at T sub Ci, then it leaves at T sub C naught, which there is no possibility to be higher than the exit temperature. And in general, all the heat exchangers are preferred to have a counterflow. And in the counterflow, there is a uniform temperature distribution and they provide a good temperature difference between both fluids. So it is more efficient than the parallel flow pattern. So we now know that there are two flow uh, arrangements in the heat exchanger. The first one is called the counterflow pattern, and in this pattern we may calculate what is so-called the logarithmic mean temperature difference and the mean temperature difference, which is defined as F sub T times LMTD. And F sub T represents the temperature correction factor, which is presented in a graphical and mathematical expressions in the literature. And LMTD represents the log mean temperature difference. So if we substitute the values of both the fluids, inlet and outlet, in this expression, then we may get the mean temperature difference across the heat exchanger. Similarly, we have the parallel flow, and if we use the same conditions, then we will be able to estimate delta T mean, which represents the mean temperature difference. And if we take uh, an example for a typical values, we have found that the mean temperature difference for the counterflow is greater than the parallel flow, and hence we need lower area for the heat exchanger for the counterflow when compared to the parallel flow. And that means in a typical calculation, if we have specified the heating load and we know the conditions of the inlet and the exit temperatures for both fluids, then finally we may estimate the surface area required. For the counterflow, we have an effective length for the heat exchanger is around 800 millimeters. And for the same conditions, if we choose the parallel flow, then the effective length of the heat exchanger will be 950 millimeter. And that means surface area bigger, then the cost will be higher, and at the same time, the maintenance and other parameters during the operation of the heat exchanger will be higher than that the required for the counterflow range. This is just to show a comparison which flow directions are preferred. So this example shows that the uh, counterflow arrangement is better than the parallel flow arrangement. To describe the results which we have got through this episode about the flow arrangement, I think we have to take a practical example and to show this effect. Let us consider double pipe heat exchanger where water at 30 kilogram per minute flows through the inner pipe, and it was at a temperature 30 and leaves the heat exchanger at 50 Celsius. In the annulus, we have engine oil at a temperature 90 Celsius, and it is cooled to 60 Celsius. So in effect, we are cooling the engine oil by using a cooling water. And let us put a question about the difference between the logarithmic temperature difference in the case of a counterflow and the parallel flow arrangements. In the counterflow, we have the engine oil enters at 90 and leaves at 60, and the water, the cooling water, enters at 30 and leaves at 50 Celsius. And they are flowing in an opposite direction. Delta T1 at the first end equal to 90 minus 50, and that gives 40 Celsius. And delta T2 represents the temperature difference at the other end. It is equal to 60 minus 30, and the result will be 30 Celsius. If we apply the logarithmic mean temperature difference equation, delta T1 minus delta T2 divided by the natural logarithm of the ratio between delta T1 and delta T2. If we substitute these values of delta T1 and delta T2, then the final results will be 34.76 degrees Celsius, which represents the logarithmic mean temperature difference for the counterflow. Similarly, if we consider the parallel flow, and we have first end, we may calculate delta T1 is equal to minus 90 minus 30, and then the result will be 60 Celsius. And delta T2 will be at the other end, 60 minus 50, which equals to 10 degree Celsius. Then if we apply the logarithmic mean temperature difference, we will end at a value which is shown in this numeric analysis. So in effect, we have the mean temperature difference in the counterflow is greater than that of the parallel flow. And if we apply the general form for the energy of heat transfer in heat exchanger, we will expect that the surface area of the counterflow will be less than that of the parallel flow, and of course that will lead to conclusion that the cost of the counterflow is less than that of the parallel flow to produce or to manufacture a heat exchanger having the same heating or cooling load of the process fluid. So in effect, the cost, of course, that will cover the cost of material, machining and manufacturing, and maintenance, and at the end we will end with a heat exchanger which will be more economic to have the counterflow as compared to the parallel flow heat exchanger. Finally, my friends, we have arrived to the closure, which gives a summary for the content of the present video. We have passed through the description of fluid flow in heat exchangers, the flow pattern in a heat exchanger, how should they be? And finally, we compared the flow pattern in heat exchangers where we have the two flow types, the counterflow and the parallel flow, and we have arrived at the conclusion where the counterflow is preferred and is better than what we have for the uh, parallel flow. We have some useful resources in the description box are linked with a PDF file. You may make advantages of them. If you think that the present video and its content is useful to you and others, please subscribe to the channel and share it with your network, your friends, and let us succeed together in the project of this channel. Bye bye.